Welcome back to ECE 441A, 541A. Homework number 8 is due on Thursday, tomorrow. And lab number 3, project number, or deliverables 2 and 3, those are due on Wednesday, the 7th of December, as are teacher course evaluations, as are homeworks 9 and 10. So a lot to do, and then a week after that, on Tuesday, not quite a week after that, Tuesday the 13th is our final exam in this room from 10:30 to 12:30. I have posted a couple more notes and lectures available for the phase lag controller design after the lecture from Monday, which was lecture 9.1. Then there's a MATLAB example of that system that we were trying to control at the end of the last period. That's 9.1M. And if you want to see the derivation of the steady state error, that's 9.1E for extra or air, however you want to use the E. But that's the announcements for today. What I'm planning is to finish up Bode plot controller designs today, and that will be the phase lead controller. Obviously, I may have to give you some additional material there, and then we'll start with state space design techniques, which is really sort of what you were doing in lab number 2. You were measuring the state variables, scaling those up, feeding those back into the system to locate your closed loop poles almost arbitrarily if your system was controllable. And that's where we are headed in Chapter 11, which is state space design. And if you're holding off on doing lab number 3 because you don't have lab number 2 yet back, don't hold off. You don't need lab number 2 to complete lab number 3. You simply need the transfer function from lab number 1 to continue for lab number 3. What I want to do then today is review the Bode plot as far as we're really only looking at 2 in this class, phase lag and phase lead. When do you do those 2? What's sort of the defining condition for selecting between a phase lag or a phase lead? And then we'll go through the procedure for a phase lead controller design. Contrasted with how we were designing controllers in the root locus. The root locus, we typically found from our design specs desirable locations in the S-plane, and that basically fixed our transient behavior. Then we fixed those poles and we just checked our steady state error as an afterthought. With Bode plot, we're really doing the opposite. We're making sure that our steady state accuracy is fixed or meeting the design specifications that we want by selecting the gain in the system. That's the first goal. Then the second goal is to adjust the phase margin to try to achieve the transient behavior that you're interested in. And how you shape that transient behavior or how you adjust that phase margin is determined by whether you can slow down the system, which means use a phase lag, or if you don't want to slow the system down, you're not necessarily speeding it up much, but you don't want to slow it down, then you're going to use a phase lead controller. It's Wednesday, I believe. Is that true? Although there's not a whole lot of you here for me to check that, but I think these are the right faces that I should be seeing on a Wednesday. So if it's a Wednesday, we have our thumbs up. No, I want to give you a rule of thumb for translating this zeta value, this damping ratio, into phase margin. You've probably become a little bit more comfortable with zeta. If I said, I want a zeta of 0.7, what would that make you think about in terms of transient behavior? If I said a zeta of 0.7. 45 degrees. In the transient response, what does that mean for a pure two-pole system? A 45-degree angle on your closed-loop poles, or a zeta value of 0.7. Do you remember? Do you have that figure memorized? Where does that zeta value of 0.7 intersect with that curve? If you don't remember, 5% overshoot for a zeta of 0.7. A zeta of 0.6 was about a 10% overshoot. In Bode plot design, you may be given a zeta or a percent overshoot, and you go, well, wait a minute. With Bode plots, I usually like to concentrate on phase margin. A rule of thumb, then, is that the phase margin in degrees is proportional to zeta. Again, this is a rule of thumb. It's very rough, but you can now scale your phase margin in degrees by 0.01 to obtain a zeta. Typically, we're going the other way. Somebody might say, I want a percent overshoot of 5%. And you go, oh, well, that's consistent with a zeta value of 0.7. So now I have a zeta value of 0.7, my phase margin. Oh, I want to try to achieve a phase margin of 70 degrees in this Bode plot design approach. That's what I'm trying to illustrate with this rule of thumb, and that's given in equation 58 in chapter 9 in the 13th edition of Dorff and Bishop. That's on page 618. But that equation is just zeta is equal to 0.01 times the phase margin. All right, we have a couple of fill-in-the-blanks quiz to get us going. We need to be exercising to keep warm. 2 controller types, and that's all we're focusing on in this class, phase lead or phase lag. So even if you weren't wanting to exercise, you could maybe pull out a coin. You have 2 options, heads or tails. If one can slow down the system response, and I've already given you this answer, what kind of phase blank controller are you using? And this is the S-plane plot of those poles and zeros of a phase blank controller. They are near the origin. What kind of a phase controller are we using if you can, or if you are allowed, or if it's okay to slow the system down? Phase lag. You win what's behind door number 1, which keeps opening, but that's okay. We only have 2 doors in this class, so it's very appropriate for phase lag and phase lead. Now, this one's very challenging. If one does not want to slow the system down, then what kind of controller do you want? All you have to have here is a little memory. What did we just say before? We said phase lag. What's the other one? Phase lead. Now what I may be asking you is, what does the pole zero pattern of a phase lead controller look like in the S-plane? How do you put those on your S-plane? We just have a first order controller. We have 1 pole and 1 zero. Where do those get located in a phase lead controller? Where in the S-plane? And now this is generic. This is just a generic relationship between your poles and zeros of your phase lead controller. How would you put those into the S-plane? First off, you have 1 of each. Where can you locate 1 singularity in the complex S-plane? It has to be on the real line, right? If you just have 1 zero, not 2, then you can only be on the real line if you just have 1. 2, you could have them in complex pairs, complex conjugate pairs. But if we just have 1 zero, we know it's on the real line, and we have 1 pole, we know it's on the real line. Now we just need to know which one of those, pole or zero, is closer to the origin. And this is what you were doing with the root locus design. This is a review for the final exam. Where did you locate your zero in a phase lead controller relative to the pole? Was it closer or farther away from the origin than the pole was? I guess we could get out our coin again. Ouch. Didn't it look something like that? You were trying to pull the root locus further into the left half plane. Ideally, you would like to just put a 0 there to make that attraction happen, but we can't just put a 0 in as our controller. We don't want a derivative action in our controller, so we roll it off with that pole at higher frequencies. So the pole is further away from the origin than the 0. And how those are spaced depends on how much phase angle we want to introduce into our Bode plot design. But this is now trying to connect our Bode plot and root locus design approaches. Here is an example of a phase lag controller. The blue line is what we have in our Bode plot once we've satisfied our steady state air spec. We've determined our K, and that's really just raising and lowering that magnitude curve. If we adjust the gain K, that doesn't change the phase. It just raises or lowers the magnitude curve. We've now set the gain to meet some steady state air spec, or that's now focusing on this low frequency behavior. We've now fixed the gain, and in this case, what's that blue line doing if we went to a lower frequency? If we went left in the top plot that I've now highlighted in yellow, how is the blue curve moving? Is it flat? Is it going down as we go further to the left? Is it going up as we move further to the left? And how can you tell? I'm trying to give you hints if you're in the classroom. They're maybe not very effective hints, but hopefully you were imagining this strange instructor in the front of the room stretching and pointing to minus 90 degrees on the phase plot. What does that tell you if you have a phase of minus 90 degrees? And it definitely looks like it's leveling off as you go to smaller and smaller frequencies. What's an angle of minus 90 degrees tell you at low frequencies? If you have a pole at the origin, what's a pole at the origin do in terms of your magnitude response? Does it break? No, it never breaks. It always is sloping at minus 20 dB per decade. Meaning this blue curve, if you had to extend it, is still sloping at 20 dB per decade, and it's coming down from above. It's going really high in terms of dB at lower and lower frequencies. And what does that do? That annihilates any error due to a constant input in your closed loop system. It also allows you to track with a constant error some ramp input, that type 1 system. That's giving you a type 1 system. But in our case, what we wanted to do is design a phase lag controller, which means we can slow down the system, which means that omega sub g can be moved to the left. Where is omega sub g? I've put all these arrows on here. I had it all labeled, and then I said, well, that's no fun. Let me erase that and have them complete it for me in class tomorrow. So where is omega sub g? That's how did we define omega sub g? G stands for gain. So omega, that's the gain crossover frequency. For the blue curve, where is that? Which of these 4 arrows is it? Is it the one on the far left? Somewhere in the middle? Is it 1, 2, 3, or 4? Counting from left to right. So omega sub g is used to, we have 2 crossover frequencies, don't we? We have a blue one and a red one. Omega sub g was for the blue curve. Where is the blue curve going through 0 dB? Isn't it the fourth arrow? So this is now omega sub g. And with a phase lag controller, we're saying we can make omega sub g, or the gain crossover, lower in frequency. We can slow our system down, which means that we are introducing poles and zeros to bend the magnitude plot so that it kinks and it comes down and crosses the 0 dB line at a lower frequency. What's the third arrow representing? What did we call that? Do you remember in our design? That was our new gain crossover frequency, omega sub c prime. What is this first singularity pointed to by the arrow that makes the red curve now move off of the blue curve? Now we've compensated. This red curve is our compensated Bode plot. That's after we've introduced the controller, and the controller consists of one pole and one zero. What happens at the first arrow? Which way is the curve going? Up or down? That gives it away. So it's going down. What's down? Poles. So that's a pole that happened right here in our controller. We introduced that so that we now drive the magnitude lower more quickly in terms of frequency as far as moving from left to right. And now what's left? What's the kink that takes off that slope after the pole? That's our zero. Which, if we wanted to try to find the phase margin of the uncompensated system, where would we find it? The uncompensated system is the Bode plot with the K to meet our steady state air spec. That's the blue curve. How would we find the phase margin in this system? Uncompensated. Which omega do we use? Again, we're trying to look at a 1 at an angle of minus 180. Where are we at a magnitude of 1 in our magnitude plot? At what frequency? At omega sub g. That's the blue curve that we're interested in. Now we go down and we say, how close to minus 180 are we with our phase at omega sub g? Very close, aren't we? We hardly have any phase margin in the uncompensated system. So what we've done is we've now lowered our magnitude curve to reduce our gain crossover frequency to back us up in terms of frequency to make our 0 dB frequency crossing lower, and now that allows for us to have a bigger phase margin when we cross the magnitude at 0 dB, or the 1 at minus 180. And the compensated, this is now the phase margin compensated. And this difference between the red curve and the blue curve at that omega sub c prime is why we introduced the safety margin in our design process. The controller's phase hasn't yet finished contributing its phase at that particular frequency, omega sub c prime, because our straight line approximations are just that, they're approximations. It actually keeps contributing phase a little bit beyond a decade before and after the actual break frequency. But on the final, you should be able to find the phase margin and the gain margin. In this case, what's our gain margin? Where is our phase crossover frequency? It's about omega sub g, isn't it? The phase crossover frequency in this picture is right in there. It's where the phase curve crosses minus 180. We would then go up and see, can we increase our gain at all, any, to get any gain margin? And it's very small in this particular system when we hadn't yet compensated it. That's the phase lag. We're allowing our magnitude to curve to cross 0 dB at a lower frequency. We're tolerating a slower system. In the phase lead, we don't want to do that. So that in a phase lead, this is exactly the same original Bode plot. The blue curve is the same. Now we are not wanting to make the 0 dB crossover frequency of the compensated system smaller. We want to make it maybe a little bit bigger. Meaning, the blue curve, I don't know how that happened, but somehow it got covered up with my writing, but that's the compensated curve, or uncompensated curve for the blue plot. What's this first arrow pointing to in terms of a element or a factor in our controller? Which element? Is it the zero element or the pole element? That's our zero. So we have our zero starting first. Then what's the second arrow pointing to? That's pointing to omega sub g from before. And what's the third arrow pointing to? That's where we have our pole of our compensator. And then the last arrow, which is now pointing to the compensated Bode plot, we've now moved our cutoff or our crossover frequency a little bit higher, but now we're going to call that, now I better look at my notes to make sure, I think we call it a little bit something else. Well, I think we are going to be calling that omega sub m. But in this case, we could just as easily, to be consistent with before, say it's omega sub c prime. And this, now do you see what our phase margin is in the red curve? Now we come down from omega sub c prime, our new crossover frequency, and now, even though with the uncompensated system we didn't have much phase margin, now we do have some phase margin, and it's at a higher frequency than what the phase lag phase margin was giving us. What we want to do now is work with finding out or coming up with the procedure to specify these particular zero and pole locations in our phase lead controller design. That's what we want to do now. So let's look at that process. Or the phase lead with Bode plots. As a reminder, we're using this technique, or this technique is useful when the phase margin needs to be increased without lowering the gain crossover frequency. By not lowering the gain crossover frequency, we're actually not wanting to slow the system down. That's our objective, is to increase our phase margin without making our gain crossover frequency lower in frequency. The transfer function looks very similar to what we've had before with the phase lag. It's just now our zero is closer to the origin than our pole, And so its time constant is longer, that's the alpha tau, than the pole is. Or you might want to write this as 1 plus s over z sub c, or and 1 plus s over p sub c, where z sub c is the controller of your, is the zero of your controller, and p sub c is the pole location of your controller. Here's the procedure, and this will be helpful in homework number 9 to know these different procedures. And the first goal of a Bode plot design is to try to achieve the steady state air spec. And that requires that we figure out what gain we need. So the first step is to determine the gain constant needed to satisfy the steady state air spec. The next step is then to use that gain to plot your uncompensated Bode plot. So step 2 is plot the uncompensated. That's been the blue curve in our previous illustrations. Plot the uncompensated Bode plot using the gain that we just determined in step 1. The third step is now to figure out what our phase margin is. Determine the phase margin. For the uncompensated system. And that's the phase margin in the blue curve that we've been looking at before. And let's call that P phase margin sub U for phase margin uncompensated, or PM sub U. If it turns out that you luck out and that phase margin is big enough to meet your design spec, you're done. You don't have to go any further. You've basically been able to satisfy your design specs by adjusting the gain in your system. If the phase margin is sufficient, and that's the PM sub U, then no phase lead controller is needed. On the final, it's probably not going to be sufficient, so if not sufficient, determine the necessary phase or maybe I should say determine the necessary amount of phase needed to satisfy the phase margin specification. Where now we're simply wanting to know how much phase do we need to introduce above and beyond what's already there. And I'll write that then as phase margin desired. That's maybe what somebody specifies. Maybe they say, I want a 50-degree phase margin, and maybe your uncompensated phase margin was 20, then you need 30 more, but because of what we know happens with respect to the angle of our controller, let's introduce a little bit of a safety margin. So in addition to maybe this 30 degrees, we up that and say, let's add in 35 degrees because we know that our controller is going to actually not quite be done with contributing phase at the crossover frequency. So phase or phi sub SM is a safety margin in degrees, which is needed to account for the shift of omega sub g. And omega sub g actually went to a higher frequency with the omega sub c prime. For the shift of omega sub g to a higher frequency. And typically we may use a safety margin of 5 degrees or 10 degrees. We just don't want to get silly because we really can't introduce much more than about 60 degrees with a single stage controller. If you look at the book, it's 70 degrees, but that's very extreme, and you probably don't want to be introducing or having phi sub m equaling 70 degrees. If you do, then you're going to have to probably introduce 2 stages of your phase lead controller. Now that we have phi sub m, what we want to do is calculate the pole zero separation in our controller. So now calculate the pole zero separation, which will supply the additional phi sub m that's needed. And we have an equation for that. We can now find alpha, which is the difference between our pole location and the zero location. Alpha is now 1 plus the sine of phi sub m over 1 minus the sine of phi sub m. And that's actually then derivable from an equation in the book, which is equation 11 in chapter 10. That isn't equation 1011. This is now derived from that. They have a formula for sine of phi sub m in terms of alpha, and I just flipped that around. I solved for alpha so that now all you need to do is go from step 3 to step 4. And if you wanted to see the relationship between phi sub m and alpha, you could see that in figure 10.4. Now what we want to do, now that we have the pole zero separation, now we need to find out where do we pin the pole and the zero down. All we have right now is the separation between the zero and the pole. On the Bode plot, this is now on the uncompensated Bode plot, find the frequency at which the gain has a value equal to minus 10 log of alpha. So now you look at that blue curve, and you maybe on the left-hand side where you have your axis labeled, you find this value of minus 10 log of alpha. Let's say it's minus 8. You find minus 8, you scroll over until that intersects the Bode plot, and now what frequency did that happen, or where did that happen? We'll designate that frequency, or call that frequency omega sub m. And that's our new gain crossover frequency, or it will be close. Designate this frequency omega sub m, the new gain crossover frequency. And omega sub m actually is halfway between the pole and the zero, but that's on a logarithmic scale, so it's really the geometric mean of your pole and zero determines this omega sub m. And what we now want to do is use that information to calculate the pole and zero locations. Calculate the pole and zero locations by calculating the time constant which in our controller we were labeling as tau, where tau now is defined to be 1 over omega sub m times the square root of alpha. We calculated alpha from our pole zero separation. That was in step 4 to give us the phase margin or the angle that we wanted to add. We found omega sub m graphically. Now we have those two values. We can calculate tau, and this now gives us our controller, which we defined in terms of alpha and tau. There's the zero location, depending on alpha and tau, and our pole. And this is now our phase lead controller. And obviously you would check the phase margin of this compensated system, the red curve, and if it's not sufficient, then you have to try to increase that phi sub m by going back earlier in the design steps. Let's look at an example of applying these steps to create a phase lead controller. Suppose somebody gives you g of s, and that's k over s, s plus 2. And typically, if you're not told, you're going to have this classical block diagram configuration where g is now given, maybe not completely, maybe we have to find the gain k, and we need to find g sub c. And how we find k and g sub c is obviously going to depend on the design specifications. Suppose somebody now says, here's what I want you to accomplish in the closed loop by introducing a controller g sub c. Suppose they say, 1, I want a steady state error due to a unit ramp. I want that to be less than or equal to 0.05. And then let's say they also want a phase margin greater than 40 degrees. And the third spec really is do not slow down the system. Up until that third specification was given, you could have accomplished this with either a phase lead or a phase lag controller. But when they say don't slow the system down, now they're telling you attack this with a phase lead controller. What's the steady state error if our closed loop system is stable? Well, based on what you know about the root locus design, is this system stable for any particular values of gain k? Are there values of gain k that will stabilize this system? Do you see the classic root locus? You start at the origin and -2, and those come together. They break right at -1, and they just go up as you increase the gain k. This particular system has an infinite gain margin. You can crank up the gain as much as you want, and you'll never go unstable. So, with that statement, what's the steady state error due to a constant input? Why am I worried about a unit ramp? Why don't I worry about a constant input? What's my steady state error due to a constant? It's 0. Why is that? And now you can answer that by saying something about your plant. Your plant is a type blank system. What's the blank? How many poles do you have at the origin? 1. That now determines your system type. What's the system type? It's a type 1. If you have a type 1 system, and you can get that type 1 system either with putting a pole at the origin in your controller, or it's already there in your plant. If you now have a type 1 system, then if your closed loop system is stable, you're going to have 0 error due to a constant input. Your transient may be awful, but that's maybe not the issue. But here, it makes really no design effort to say, oh, give me 0 error due to a constant input. So now we're saying, let's look at how close we can get to a ramp in the steady state. And now we're saying make that distance 0.05 or less to track a ramp input. So let's now find k in our system to make that happen. That's step number 1. In step 1, we want to find k using the air steady state specification. And in fact, the steady state error is related to the velocity gain constant by E steady state is 1 over k sub v. And if you want to know where that's coming from, that's in the book, or I've also talked about it in that extra lecture, which is lecture 9.1e, or I derived that relationship. And how do we define the velocity gain constant? K sub v, do you remember? That's also in that lecture. So this is similar to the DC gain in a way in terms of the formula, except now you're looking at the limit as s goes to 0 of s g of s. Or in this case, we're looking at the limit as s goes to 0 of s times k s plus 2. Those s's cancel, and if I let my s vanish, I end up with, in terms of my gain in my given system G, it's related to k sub v by this relationship. K sub v is k over 2. And what did we want for k sub v? Well, that was given to us from our steady state error relationship. We have air steady state is 1 over k sub v, which we now know in terms of k is 1 over k over 2, or this is now 2 over k, and we wanted that to be less than or equal to 5/100ths. So that now we can find that if we solve that for k, we have 2 times 100 divided by 5, and let's just say that, well, or K needs to be bigger than or equal to 40, let's just make it equal 40. Let's not get too crazy with how big we make our gain K. Let's say we just want to try to satisfy, just meet that particular steady state air spec. Is it clear where that gain came from? That's the very first step you have to work through before you can sketch your Bode plot. Now, you could sketch your Bode plot. Let's say that you get on an exam, or maybe you're in an interview and somebody says, oh, can you sketch the Bode plot of this system and have a steady state error of some amount? You might say, well, let me not worry about the steady state error. Let me just first sketch the Bode plot. And they go, well, how are you going to do that? You just have a K. You act very knowing and you say, I don't really care. I'm just going to set a K of 1, or I'm just going to set a K of 10. Why does it not really matter? Because all you really have to do, once you've sketched the magnitude curve, you just have to slide it up or down depending on what the K actually ends up needing to be. So you could pick a K of 1 and sketch that. And now if you subsequently find out, oh, I need a K of 20, now you just take 20 log of 20, which is what? What's log of 20? What's log of 2? 0.3, isn't it? So now log of 20 is 3. So now we have 20 log of 3. So 20 times whatever I was at. Now I've lost my whole train of thought because of origami. What do we have? But now we would just raise that gain curve by the appropriate dB that we just calculated. Is that clear? So now we have K of 40, and we've actually succeeded with our interview question. So now if we let K equal 40, we now have a G of S with a fixed gain. And what structure is this controller in? Time constant or pole 0? Pole 0. And which structure would we like it to be in to sketch the Bode plot? We probably want it in the time constant form, which we can now have. We can now factor out that 2. And now we have our system with which we can sketch. And if you cheat like I did before class and do the Bode plot or do the MATLAB, then we can maybe, if it cooperates, we now have our Bode plot for that gain of 20 over S times the quantity S over 2 plus 1. Does this Bode plot look consistent with that system? Where's our angle at low frequencies? Where should it be? What was our system type? Type 1, that had a pole at the origin. What does that say the phase is at low frequencies? That pole at the origin is contributing minus 90 degrees for all frequencies, and that's where we're starting, isn't it? What's the curve look like magnitude-wise at low frequencies? Is it sloping at 20 dB per decade? Yes. And so this is looking consistent, and where are we ending up on our phase? Minus 180. What's our pole 0 excess in our system? It's 2, isn't it? So we have 2 more poles than zeros, 2 poles, each of those giving us minus 90. We're going to end up at minus 180. So now what we have to do is we want to introduce a 0 Whoops, didn't want to do that. We introduce a 0 and then a pole, and what's that going to do? That's going to shift this curve so that we get more of a phase margin that we want. And that's what I will try to put together after this class and make available on the course website. But that's where we're headed with a phase lead controller.